Good evening to everyone. Am I audible?
Yes, you are absolutely audible.
Thank you, sir. I welcome you all for the second day of the Faculty Development Program on Future Innovations, Energy and Sustainability. We sincerely appreciate your continued participation and enthusiasm throughout the program. So we now proceed to the first session of the day. And we are pleased to have Dr. Arghya Mitra, sir, resource person for this session with us. A very warm welcome to you, sir. Dr. Mitra is currently serving as an assistant professor in the Department of Electrical Engineering at VNIT Nagpur, with over 23 years of experience in teaching and research. He completed his undergraduate studies in electrical engineering from Jadavpur University, followed by a master's degree in electrical engineering from the University of Calcutta, and later obtained his PhD in power and energy systems from the Indian Institute of Technology, Kharagpur. For his doctoral research, he was recognized with the prestigious Power System Operation Corporation Award, which acknowledged his contributions to the field of power systems. Dr. Mitra has authored over 80 research publications, including contributions to the reputable international journals such as IEEE, Transactions, as well as 2 book chapters and a national patent granted in 2024. He has been involved in several national and international research projects funded by agencies such as the Ministry of Education, SPARC, DST Horizon 2020, MHI, and BART, contributing as principal investigator in the areas including global grid architecture, renewable microgrids, and EV wireless charging technologies. His primary research interests include power system dynamics and stability, renewable energy grid integration, and microgrid energy management and stability. Dr. Mitra will be speaking on the topic Energy Management and False Data Detection in Microgrid Environment. Sir, we request you to kindly take over the session.
Thank you very much for this generous introduction. Am I audible to everyone?
Yes, sir.
Okay, so let me share my screen now. Is my screen visible to all of you?
Yes, screen is visible.
Okay. So very good evening to one and all present for this online faculty development program, OFDP, on future innovations, energy and sustainability. Today, my topic of discussion is sustainable microgrid environment. So I will discuss this in 2 phases through energy management and false data detection. So the first one, this energy management part is from a real case study, which was basically a part of one of the R&D project, Horizon 2020, funded by DST, in collaboration with European Union and several institutes from India and abroad. The leading institute for this particular project from Indian side is IIT Kharagpur, and VNIT was acts as one of the partners. And leading institute from abroad is NTU, National Technical University Athens from Greece. So the task related to this particular R&D project was deployment of microgrids at 4 different sites. 2 are in India and 2 are in Europe. So those 2 microgrids in India, one is situated in Goramara Island in West Bengal, another one is Keonjhar in Orissa, and Kithnos and Bornons are the other 2 places where the microgrid deployment were there. Basically, I should not say that deployment of microgrid in the European sites. There were existence of those microgrids. Only our task is to make them smarter. And the Indian sites, we need to start from scratch. So I'll just, my contribution for this particular project was from the power system aspects, that starting from the handling the renewable sources, the stochastic nature of this renewable sources need to be taken care, and then how the energy can be managed along with the stability and the black start. So I'll just make this presentation with aspect from that how we have forecasted the different energy vectors, including the sources and the loads, and how we have managed it as in smart way. So all these things are being implemented in these projects. The second part, so here the microgrids, what we are talking about are basically to make them sustainable. So it's not only that we have deployed and then we just don't think about that how it will sustain. So there is a business model that it should operate even if there is no funding. So they can generate some revenue, and whatever the maintenance and operating costs are there, it can be catered through those revenue generation. Essentially, these microgrids, from the Indian perspective, those two Indian microgrids, they are the not only the microgrids, but they are also working as a charging station for the EVs. So this is the first part. These 4 microgrids, all the 4 microgrids are not connected with the national grid. So it is they are working in isolated. So they are having some different challenges and applications. The second part, which is again another important aspects where the microgrids may be connected with the utility grid. If during that transmission of the that exchange of energy between the grid along with the utility grid, if there is somehow the communication process has been tampered and false data has been injected, so what would be the impact on the dynamic pricing? So how to detect that false data and take care of it. So that all also being discussed in the second part of this discussion. So these are the 2 parts I have divided for today's discussion. So starting with this energy management in grid integrated solar PV based microgrid working as smart charging station. So this first, what was the task is basically you need to design the system. Then there are 2 parts. So one is that forecasting of all the energy factors like load, solar PV, wind power, and the system stability. These forecasted variables are then used for 2 purposes. One is this demand response and demand side management. And this stability system stability part is basically with that DC microgrid stability and black start. So black start means when we are starting from nothing. So there is no energy, no load, nothing was there. So we just switched on, and the how the system will operate within the black start. And even if it is operating and something has happened, some natural calamity and all, we need to switch off everything. So again, we'll restart it. So how the system will take care, how it will operate to its steady state. So that was being considered in this black start. So we're not concentrating these 2 parts, the stability and the black start, but for the time being in this discussion, we'll only focus on this demand side management. So after integration of all this study, then the development of the overall control algorithm that need to be implemented and tested and deployed in the Indian demo site. So that is being the workflow of the task that I was handled in this particular project. So what is the problem statement specifically for this today's discussion is that energy management tool for energy vectors. So we have developed a tool where this not only the forecasting was done, but also with the help of this forecasted energy vectors, we did some kind of a smartness. We introduced some kind of a smartness in the system through which the revenue generation is possible, and at the same time we can introduce that demand side management and the demand response analysis for making the grid less stress. So the tear down, we are just objectives can be made in that way that it should capable of serving any microgrid, should allow the integration, and should be adaptable to various load and energy factors. The thing is that we are having 4 sites, so we developed one strategy, and that strategy should not be confined to any particular area. These energy factors are being handled, so renewable energy sources as well as the load, as I told you, and the forecasting of all the energy factors and the demand response for the demand side integration. So the end-to-end product cater to all the needs of an isolated microgrid are being taken care. And as I told you, it was the project which is EU India re-empowered project from the funded by DST Government of India. So let us first introduce the locations. So these location details, first one, as I told you, is the Ghoramara Island in West Bengal, where there was no grid, utility grid has reached till date. So there were no electricity, so there were no loads at all. There are few small loads because of this isolated solar PV, rooftop solar PV and all were there. But the households, the markets, the commercial loads like some school or hospital, and some poultry farms, some agricultural ways of absorbing of those electrical energies, that probability were there. So that was being catered with the help of this project. So deployment of actually the microgrid was deployed, which essentially was integrated with the solar PV, wind turbine and battery. So the consumption, as I told you, could be like the non-critical loads, like residential household loads, commercial loads like market, school, hospital and poultry farm are considered to be the critical loads, because we need a constant power supply to these different type of categories. The challenging part was there, as because there was no such microgrid or electricity is there. To start a forecasting, it's a real challenging part. We don't have, from the point of view of the energy vectors of sources, so we can get data from PVsyst. So we just take data from the previous maybe 2 years, 5 years, 10 years data can be taken, and we can have that ability to forecast that. But how can I forecast the load? There was no load at all. So that was a challenging part. So what we did is that we know that how much power can be generated through these sources. So we know that what could be the load, that maximum load can be connected in these grids. We also decided that what would be the tariff for the revenue generation purposes. So households, it was ₹50 per month per house, assuming that 1,000 houses for the calculation purposes. So there were almost like 1,100 families were there in these three villages of that island. The commercial loads are being ₹100 per month per load. Assume such 6 commercial for the timing that we assume, the study has been assumed in that manner. Number of inhabitants, as I told you, is 1,100 families, so total 3,000 residents were there. This is a cyclone prone area, so every time now the cyclonic environment are being frequently being hampered these locations. So there were other partners who were taking care of that. All these wind turbine and all, they need to be, the structure need to be, that cyclone withstanding capability must be there. So though it was written that it faces extreme weather conditions every 2 to 3 years, but now the frequency has increased nowadays. The next one is Keonjhar. It's a beautiful location. The Ghoramara is also very beautiful location was there. The scenic beauty was very good there. Keonjhar is at the top of a hill inside a jungle. So there are also two villages were there. The area is 202 hectares, 75 houses with 300 populations. So this is the number of inhabitants. It is oppressively hot in summer with high humidity. Where we are having, as because it is inside the jungle, so we are not using wind as one of the targeted solar generation. Instead of wind, we are using that biomass and biogas. That is biomass is largely available because of that jungle area. So we collected that, and then the biomass capacity 10K peak and biogas capacity is also 10K peak has been integrated along with the solar PV. And the tariff at that region is decided separately. For the residential household, rupees 80 per month, and the commercial consumers, rupees 10 per kilowatt hour. So that is how. The Keonjhar island was being taken care of. This Goramara island is totally being taken care by IIT Kharagpur, and this Keonjhar location is being is mentored by IIT Bhubaneswar. So IIT Bhubaneswar is also one of the partners for this project. Coming to the other island, Bornholm Island, which is in Denmark. Here, total number of inhabitants is approximately 2,500. It's a coastal area. There are solar PV, there are biogas plant, there are wood chip powered boiler generators, and there is a fossil fuel generation also of 58 megawatts. So it's not fully, in that sense, fully green energy. A little bit of fossil fuel based generation is also there. The good part is that we have already there were microgrids, some recording devices were there, so we get some data. So it was easy for us to predict the load in case of the Bornholm. The other island is in Greece, Kythnos Island. It is 608 inhabitants were there. And the pilot project has been taken care by the leading institute, which is NTU, as I told you, and from the European side. So there is again solar and wind mainly are the resources for this particular location. So this is more or less the background we can start with for these 4 locations, 2 in India and 2 in European side. Now, ML-based forecasting needs some data set. So for site Goramara site, now we have that PV data set and wind data set which were collected from the PTCist, and the load consumption data set, it was unavailable. So we just assume some random load profile based on the daily energy generation, because we know that how much energy we can generate. So based on that, we are going to provide the load. So we know that what load will be used at what time. So depending on that, practically, though it is tell that it is random load profile, but it is basically on the practical assumptions that load profile has been created. In Keonjhar also the load was not available. So again, there was a random load profile based on the daily energy consumption. It was being considered. For Bornholm, the PV dataset, wind dataset, and the load consumption dataset partly available. And for Kythnos, the load consumption dataset is again partly available. Though it is written as that unavailable, but there are partly available dataset was there, not fully. So this data, obviously, how many data points are there, depending on that how accurately you can forecast your energy factors. That depends largely on this, that how much data points that you are considering for the purpose of this forecast. So what ML algorithm that we're using? If you people have some idea about machine learning, so there are several methods of machine learning. We have taken one deep learning method as that LSTM, long short-term memory. Now, why this has been chosen? Because it is the long short-term memory. It has some advantages. It can handle beautifully the time series data. Mostly these energy factors based on this seasonal impact are there, and the load is also being seasonal impacts are there. So all these keeping in mind that LSTM is found to be most suitable for the forecasting for these kinds of energy factors where the data are time series based. And long short-term memory means there is a long-term memory as well as some short-term memory. So whenever there is a need of short-term load forecasting, it will just take the short-term memory and it will just forget the long-term memory. And if there is a need of a long-term forecasting, it will not consider the short-term memory. It will forget the short-term memory and will take the long-term memory instead. So both the things can be done with the help of that LSTM. So it can forecast for long term as well as for the short term. Now here the case is that we need to take care of the solar generation, the wind generation, and as because the battery capacity was already decided based on that how much space that is there, how much money has been budget is there, depending on that we have decided that how much battery can be there. So all these things is pre-decided. So only thing is that how smartly we can use the charging discharging of the storage battery. How effectively we can use that. So depending on the forecasted values, that can be done. So what we did that this is the flowchart of this forecasting of any of the energy factors, whether it is a load or source. So LSTM is being, the data is collected, and then some pre-processing of the data was there, and then we train it. So testing and training has divided. And then there is a chance of that updating the model, and then we are ultimately getting the getting some forecasted data. So what is the architecture of particular LSTM that I'm not discussing here, but there is always a chance. Further, we have not only LSTM, but also we just make a hybrid model of CNN and LSTM, and we found out that the data is much more better when it is being compared with only LSTM. So always there is a chance of that improvement. It's still open. So how the forecasting has been found with the help of this LSTM that we can see. So the first figure is showing the PV generation in the Ghoramara Island. The second figure is showing the wind generation. The blue one is basically the actual, and the predicted one is in orange. And the load profile that we have assumed. So as I told you that there was no historical data, there was no load at all. So we consider some kind of a load in that area is varying like this. So there is that load profile in the Ghoramara. In Bornholm, the PV power and the wind power, the first two figures in the left-hand side are shown, and the Kithnos, the PV power is shown, the actual and the predicted value. So it is somehow more or less we can say that the prediction was quite good. Now, what will do with this forecasted? What will do with this forecasted data? So we see that the green one is the total load. The PV generation is the blue one, and wind generation, very less wind generation. The duration when there is almost no wind, this particular window has almost no wind. So the wind generation almost zero. So this day-ahead based PV wind generation along with the total load at the Ghoramara Island is being shown in the left-hand side figure. So what is the difference, the deficit or the excess of energy with respect to the load is being plotted in the second figure. So it's the difference between the total generation and the total load. So based on that, we can understand that what could be the stress on the storage, right? So all these data are coming to the control room. So when the control room operator wish to see that what is happening, so there is a user interface model. So all these backend things are done with some algorithms and coding and all, taking data and then communicating it and then transferring it, some processing, and then ultimately have some forecasted data points. So all these things are being visible. So in a monitor, so they can able to see. So because as I told you that all these four sites are not separately considered. So one operator can able to see all the four sites, that how they are operating, what is happening. So there is a login page where the grid operator will choose that whether I'm an user or I'm a grid operator. So if I'm an user, I will see a user dashboard where the historical, all the things can be visible there. And I could have that cloud integrated master database where the forecasted variables, the battery management system, the demand response, all these things, the prices and all historical data can able to see. And if I'm a grid operator, then I first need to choose that what is the location. So this slide is for the grid operator or the utility and algorithm, where I need to check that whether I'm from Goramara, I'm from Keonjhar, I'm from Kitnos, or I'm from Bornholm. So the grid operator utility dashboard will again show you the forecasted energy factors, the load factor, the price and all, and how much is that mismatching or matching. And depending on that, we need to take care of that, what would be the demand response. Now, demand response means what? It's basically that how the demand is responding depending on the availability of the energy. So if I have less energy available and my battery is also having some limited capacity, so I cannot able to cater all the load, all the demand, right? So what I can do, I just need to shade the load. So that is obviously it is against the willingness of the customer. So I wish to enjoy the energy, electricity, but I just unable to, the operator just unable to fulfill that demand. So if I ask the customer that you yourself just shut the load or cut your load or maybe shift your load, right? So during the period when I am very stressed, the grid is already stressed. So don't just enjoy the load as you are doing in the other time window. You just cut your load or shade your load, or maybe you can shift your load, right? So those two options can be given. So that is on the willingness of the customer. I can take part, I may not take part. Now, while I am giving that opportunity that you take part, I will be in a position that now I think that, okay, my grid will be now less stressed because there is less load. But why the customer will take part, will not enjoy? Okay, so I need to give some kind of an incentive. So if you reduce your load in some manner, then you will get some incentive. Okay, so that incentive need to be find out in such a manner that that incentive again should not be a stress to the utility from the point of view of profit making, right? So I'll discuss in the next next section for false data injection in a elaborate manner, that how that being decided, what is the point of optimum beyond which you can give that incentive. But for the time being, you just consider that the incentive should not mix in such a manner that your profit becomes negative, right? It should be positive, maybe minimum, but it should be positive. Okay, so you should not be you should not create such a condition that the grid operator is basically paying and not getting. Okay, so you are giving some kind of an offer to the customer. So you take part, you will get that incentive. So the customer is reducing the load. So obviously the monthly bill will reduce, and at the same time they will enjoy that incentive. So there is a chance that the customer may take part. So if the customer is taking part, then it is not being considered at that time. It is again in a day ahead basis. So I need to know, because I know on day ahead basis that what will happen to my the stochastic nature of the sources I already have forecasted. So I know that during this period of time, this is the condition of my wind energy, this is the condition of my solar energy. So I know that my generation is less, and from the load profile, I know that maybe the load is more during this time window. So I'm asking that you take part and you reduce it on day ahead basis. They need to agree upon that, okay, I will take part in it, either load shifting or maybe load reduction. Okay, so this is how the things can be done from the grid operator or the utility end side. And from the consumer end side, so consumer end side, again, the panel will pop up, and then there is a login page. So again, it will be asked that whether you are a user or grid operator. So if you are a user, then again you need to select that whether it is for Goramara or Keonjhar or Kitnos or Bornholm. Then user database, they will see that what is my load profile, how much load I am consuming. what is the price for that load, because it is dynamic pricing, and then whether my demand response window will be open in what time, and what would be the incentive that is being offered during that period. So, and also the previous history, that how much was my monthly savings, or what would be my monthly savings, what is my electricity bill. So all these things, the PVR DR records, all will be available in the master database, which is cloud, because it is cloud integrated. So all these things can be available on that user interface and can be visible. So the user will be in a position to take a decision that whether I'm going to take part in that demand response or not. So coming to that how the pricing and incentives in a broad manner, that how it has been decided. So for Ghoramara Keonjhar, so fixed tariff, right? So as I told you that there are fixed tariffs, but in Bonam and Kitnos, the price has been dependent on it is big dynamic pricing. So this C1, C2, C3 are basically the customers 1, 2, and 3, and maybe in Keonjhar, customer 1, 2, 3, and 4. So we just clubbed a few customers and just checked it, that clubbing these customers, and ultimately giving you that what kind of load are they're using. And Bonam and Kitnos, there are historical values, then there are generation and the operational maintenance cost and other factors that will decide that dynamic pricing, and the individual metering for household, for critical loads, and the commercial loads. So there are 3 categories of the loads being considered as P1, P2, and P3. So what is that incentive mechanism? As I told you, it's on a day-ahead based pricing. So whether I am participating in demand response or not, it is being asked by the customer. So if I participated in the demand response, then I will move forward and will choose that whether I will opt for load reduction or load shifting. So one stands for load reduction and 2 is for load shifting. Okay, so from critical window to some other window, I can shift my load. I may not use in this particular period when it is being asked for. Maybe I can use my load and can enjoy the electricity in some other time. So I have that choice. So if it is being load reduction, then how much we are reduced, and the time slot for which that load reduction has been chosen. So that time slot is again divided in 2 parts. One is that critical and other one is that non-critical, right? So that critical means the grid is really facing a problem because of less generation, and non-critical is not that critical. So that is non-critical. Okay. Now the thing is that it is, as I told you, it's a day-ahead basis. Okay, so I have a 24 hours window to take part in the demand response. So if I know that how many customers are taking part in the demand response, it will be easy for the operator to manage all the energy and the pricing and everything. So if the customer is taking part, as soon as this is being floated, then the incentive given to that customer will be more. So we divided the 24 hours in 4 parts, 6 hours, 6 hours, 6 hours basis. So the total incentive, whatever the incentive has been decided, so the customer which is taken part in the first 6 hours will enjoy the full incentive. And the customer who is going to take part but take the decision later, so the second time window, they will enjoy the incentive of 80% of the initial incentive, 60%, and then the 40%. Okay, so in this manner, the incentives have been decided. Again, from the point of view of the load shifting, the reduction value and the time slot as critical and non-critical. So those are being decided, and we are considering some electricity pricing which is being decided based on this critical and non-critical. And if I'm not taking part, of course, it is a fixed price. I'm not going to get an incentive, right? So this one is showing some uh, some study with consideration of 5 such consumers. So up to this is okay. Then I will just discuss that what is the result that we are getting of this five such customers. So you see that a customer 1, they are not willing to take part in the demand response. So this we have just assumed that this could be the scenario. So we have created some kind of a randomness. So these are hourly basis, all the hourly basis, and some hours are critical, some hours are non-critical. Okay, I'm just showing here that whether I'm taking part or not taking part. Even if I'm taking part, whether I'm going for load reduction, then 1, and load shifting, then 2. So I can change my mind that initially I'm not going to take part, maybe up to 8 hours I'm not going to take part, but then I will take part and choosing that load shifting. Maybe after that I will take part and I'll choose that load reduction, considering that maybe these portions are critical. So I'll take part during this. Non-critical parts I'm not going to take part. So maybe the other customers in thinking in some different manner. So all the randomness that I have considered. So in this study, okay, and these randomness are being shown here. So whether I'm taking part or not taking part. So this is the consumer and algorithm. This is the result that I was getting. Okay. So that is how that tool has been developed. The backend part is it's over. The front end is still going on. It has some fine tuning. It still need to be done. That need to be reported and submitted. The efficient consumer response, that's the aim, and improving the pricing and incentive techniques. So, and as I told you, it's an one-stop platform for all 4 locations. That's the main takeaway of this particular study. And different consideration made for adaptability. So as it was told that the time stamping, the incentive changes and all, but it is again open-ended. If some more ways of making it smarter and win-win situation both for the operator and the consumer, so those parts are also open. So that backend is still open for upgradation. So we can see that these 4 locations are quite apart from each other, and they are all communicated through the cloud. So sitting anywhere, one can take part, one can see, one can able to take decision and can operate as an operator or as an user. So all these things will be possible in this platform. So that's the part of one of the part of this project that is being taken care by myself and my team. So that's the first part, that how we have managed the energy, how the energy has been managed. Okay. Any question from this? Then I will go to the next part. Yeah, any queries, any question or any suggestion?
So is this the ML part which you are showing as a result section?
No, it's not the real one. It's from the study part.
So, but it is specific to the that location where the case was done, or it is just a hypothetical data to explain here?
Yeah, the data what I have shown here is not the real data. The forecasted one are the real one, but the taken part of that demand response by the customers, that result was hypothetical.
Initially, 8,000 data you are taken for the study. That part is the actual one, or
yeah, that's what actual. That's what actual. That was for that location only.
okay. So it is also considered as an hourly basis.
Hourly basis. Yeah,
and
our
per user.
usage. Yes.
So, can you explain that data set? Because you are just mentioning that these are the data points which I consider for the research, but
Mhm.
how they are considered, what are the populations which are considered, or what are the constraints are
So
there?
yeah, there are constraints because you see that whenever I am handling the historical data which was available at the Bornholm site and maybe on the Kitnos site, so those data are not very good data. Data points are somehow there are missing data. There are some overlapping of data, and there are some tampered data also there. So there are some data pre-processing has been made. So and whenever there is some missing data, it was filled. So such that you can consider those we need to have some kind of a pre-processing of this data. We need to filter it out, and then that is being considered as the actual data for feeding for the training purposes and testing purposes. So the data set, I didn't show that. There is no point of showing the data points here. It's in Excel file. There are a lot of data points
Uh,
were there.
no, no, sir. What are the variables which you are considering for the data point? Like, what are the columns you are considering? Like,
Okay, so for ML forecasting purposes, LSTM, so normally we know if it is a solar, then we need to know the temperature, we need to know what is the insolation, along with that, and there are few the humidity and all. So we have several data points. Also the wind speed, also one of the data point that is being considered for forecasting of that solar. So now which one is that features need to be selected. So feature selection was another part. So which feature is important and which one is not. So that was also being done, and then the forecast has been done. So I didn't include this part as a as a discussion for this. But if you wish to know, I can separately share the things because it is available through the publications and the reports which are normally quarterly published for this particular project only. So I can share this and you can able to go through and can find it out.
okay, sir. Thank you.
Okay.
One
So
last
then,
question, sir.
yeah.
Sir, are you showing the result of your actual forecasting model?
So actual
Yes, sir.
forecasting model, the data, yeah, the results that I have shown here for the actual forecasting model only with LSTM. Now, as I told you, now later on the LSTM has been replaced with that hybrid model of CNN LSTM. So that was not shown here.
Okay, thank you.
Okay. So now the next part, which is again another important aspect of microgrid, where all these smartness are coming into the picture, means you are communicating from one point to the another point. Whenever there is a communication, there is always a chance of that false data injection for any purpose. So this FDI attack, how to detect it? Because this was not been considered previously, that what would be the impact on the false data injection on the dynamic pricing of this electrical energy if the grid is connected with a utility grid whenever there is an exchange of power. So how we can able to cater that. So for that we consider again a residential microgrid, which is essentially the rooftop solar PV is there. There is battery energy storage. And this microgrid is connected with a grid operator. So you can see that there are flows of energy, there is flow of information, and there is flow of money at the same time. Okay, so the blue line is showing the flow of power, the orange line is showing the flow of information, and the electricity price with this dotted line has been shown. So this residential part is termed as the residential prosumers because they are consuming and at the same time they are producing because their solar PV based rooftop is there. So this is the end-to-end architecture of the residential microgrid which is being considered for the study. And going inside of individual house, it's a rooftop solar PV, and then we are having that home energy management system inside. So everything maybe it's a separate study part, but it is considered that the homes or these residential part, they are smart enough. All the electrical connections are communicated centrally and can able to operate and control as per the wish of the user. So the service provider is utility grid, and the service provider is in between these residential prosumer. And the typical on-grid rooftop solar PV system with the schematic representation is shown in this manner. There is a prosumer, and there is some storage battery, and there is net meter through which the power flow in either direction can be measured, and whether the money is flowing in the utility grid or from utility grid to the microgrid, and that's being decided by this net meter. So mostly it is considered as, because the solar PV and battery both are there. So we are basically considered this as a grid assisted solar PV microgrid. So we're not wholly dependent on the utility grid. We take some assistance as and when needed, right? And we have also the opportunity, if there is an excess power generation and less load is there, we can push some power to the utility grid. That's why there is a need of a net meter. Now, whenever there is some communication, so we need to follow some communication protocol. So we may have the range of maybe 100 meter to 50 kilometers. So we can have several options, like this home energy management system inside a home, or we can have that neighborhood area network for the neighborhood area network also, which is like ZigBee technology. We have that Wi-Fi also for this home energy management system or neighborhood area network. Then for a larger distance, we can have this WiMAX technology, which is, again, these are all wireless. So Bluetooth, ZigBee, Wi-Fi, WiMAX, LoRa, these are all wireless, or we may have that wired for a longer distance and maybe for a smaller distance like PLC or Ethernet. So all these networks are either can be their home energy management system or neighborhood area network, or can be that wide area network. Right, so all these are being considered. So these are there are certain protocols that what protocol they will follow. If it is Bluetooth, if it is ZigBee, if it is Wi-Fi, if it is Wi-Fi. So out of these, any protocol, whatever we have considered, depending on our area of consideration, we need to choose and can follow that protocol for this communication technology. Now, the system schematic is something like this, that there is some local energy community with grid-tied PVPSS. We just consider some arbitrary load demand for a particular day. So there is a valley period, there is an off-peak period, and there is a peak period. Now we know whenever there is a peak period, it would be stressed. So always the grid cannot fulfill that peak period. There is some limitation of the solar PV, and there is a limitation of the battery capacity. So I may depend on the utility grid and asking some power from the grid. So whenever I'm asking some power from the grid, I need to pay back to the grid, right? So how to minimize that? Amount? So for that, we need to introduce that demand response. Okay, so valley period for this particular aggregated load demand for any one day average over 5 years has been shown here, that from 12 AM to 7 AM it's a valley period. From off-peak period is like 7 AM to 4 PM, and the peak period is from 4 PM to 11 PM. So the system specification is being considered for this particular study is like that we have a connected load of 10 kilowatt. We have some efficiency of all the inverter, converter modules, the rating of PV panel, the maximum voltage, everything was shown in this particular table. Right. So how many series parallel connections of the modules have been there. So this is the system specification for this rooftop solar PV. data set has been taken and is scaled down. So it's basically a total 5 years of data set was there from October 2012 and 2017. The study has been made based on this data set, and it is scaled down to equivalent residential sector. Basically, it is for a region where the total load is much higher than the load actually we are considering as a microgrid load. So it is scaled down as for the residential sector, and we divide the total load as prosumers and consumers in 60/40 respectively. The weather data set that contains the temperature, humidity, wind, cloud cover. So cloud cover is something. So maybe I face that question here. You can see that what are the different features data set are being considered. So hour of the day, seasonality, impact, the temperature, insolation, load demand, day of the week, humidity, wind, cloud cover, and clearness index. I'll talk more on this later on. There are the statistical description of the data set, that how much is the temperature count, the mean, the standard deviation, minimum and maximum. All this can be seen here. So we now divided it, the total data points as 3 categories. One is cloudy, other one is sunny, and the third one is rainy. Okay, so this seasonal variation being considered, if we wish to forecast the renewable sources like PV and wind. So this is particularly for the PV generation, which is largely being controlled by different kinds of seasonal or the environmental condition, which can be divided in these 3 parts: cloudy, sunny, or rainy. So how many such data points for cloudy and sunny and rainy is being shown here. Now, what's the methodology that we have chosen here? Here also, I'll show you later on that we have shown for LSTM. So weather-based classification, right? So weather variables are responsible for energy consumption, as we all know. So extreme high and low temperatures may result in higher energy consumption. So if we wish to predict the load, then we know that if the temperature varies, then the load consumption will also vary depending on that. The amount of solar radiation on that particular location, the sunrise, the sunset angle, the daily maximum possible sunset duration, and amount of cloud cover. All these are the affecting factor for the solar radiation. So energy consumption, weather, and solar irradiation data set. So they can be divided in 2 parts. One is that insolation forecasting model and the load forecasting model. So all the data points have been collected and divided in 2 parts for the purpose of forecasting model of the solar insolation, so forecasting model for the load. So whenever I am forecasting it for the solar as well as for the load, we are considering 3 separate categories of the data points: cloudy, sunny, and rainy, both for the solar insolation and for load. Ultimately, we will get that PV power generation and the forecasted load. So how these cloudy, sunny, and rainy weathers are considered depending on the cloud cover, which is defined by the World Meteorological Organization, WMO, where either we can follow these octas or maybe the tenths, where the codes 0 to 8 are being considered as fine weather, partly cloudy weather, or overcast, which is very rainy condition. So if it is 0, then there is no cloud. If it is less than 1 or but not 0, it is again fine. If it is 2 or maybe in tenths it is 2 to 3, still this is considered to be fine. So all these 3, 0, 1, and 2 codes are clubbed together and termed as sunny here. The partly cloudy portions, in octas base it is 3, 4, and 5, and in tenths base it is 4, 5, and 6. They are being clubbed together and considered as cloudy. And the next 6, 7, and 8, or maybe 7, 8, 9, 10, they are considered together and considered as rainy. So this is as per the World Meteorological Organization. So that is how the weather has been divided in 3 categories. Now coming to that insolation forecasting, so again we are using that LSTM model, and we have seen that the actual and predicted models on an hourly basis for 24 hours duration, it's giving quite a good kind of a forecasting, right? So actual one is in the blue one and the predicted one is the orange one. Now this is the solar insolation, right? Solar insolation in watt per meter square. So how I can calculate the solar PV power generation? For that, we consider that the PV power generation is based on basically this efficiency of the solar PV panel, the inverter, the converter, and the area, and some G, that is the hourly forecasted solar insolation that has been get from here divided by 1000, means it is giving you in kilowatt per meter square. We introduce one clearness index here. It is determined that whether the sky is clear. So how much clear the sky is. So that KT is basically I divided by I naught. I is the hourly global solar insolation and I naught is the extraterrestrial solar insolation, which is 1367 watt per meter square. So how much is the sky is clear, that can be decided by this clearness index KT. It is introduced for the calculation of the solar PV power generation. So we not only have included that, but we also modify that clearness index with the help of some cloud, the amount of cloud cover. So the cloud amount, which is ranging between 0 to 1 based on the categorization. So we just introduced here and that modify that KT. So this is becoming the modified clearness index, and it gives a better result, a better impact of the seasonal impact can be found out if we use this modified clearness index instead of directly finding out, directly using that KT. So that KT cap is multiplied with the previously found that solar PV, and now the actual PV power generation could be something now dependent on that, the efficiency of solar panel, the inverter and the converter efficiency, the area, the insolation divided by 1000 multiplied by that modified clearness index. Now you see that we have some solar PV insolation, which is shown here as the blue line, the first figure, and the load is shown in the orange line, right? Okay, so this part, first figure A, is for a sunny day. Is for a sunny day. If it is for a cloudy day, then the load pattern will also change, and of course the peak of the solar power is also changed. Maybe the day-wise nature of the solar insolation variation is not that much changing. It has a peak more or less at the same time, but there is a variation of the solar power generation, of course. Okay. And there is a pattern of the load which is also changing depending on the season. And the third one, the figure C, is showing for a rainy season, where of course there is a lot of difference between the load demand and the PV power generation. So here comes the use of energy storage and dependency on the utility grid. So the solar insolation and the load forecasting using LSTM along with autoencoder with some outlier filter. So as I told you that there are filtering out the unwanted data points. So LSTM autoencoder is being used here for the modeling of the solar insolation and the load forecasting. So they're taking all these inputs like hour of the temperature, humidity, wind speed, seasonality, and historical insolation data, and giving the forecasted insolation. So if I use that LSTM autoencoder with outlier filter, we are getting a much better output here. Right, so you can see now that actual and the forecasted values are shown here with the green and the blue line, and they're almost like overlapping each other. And the next figure is for the actual load demand and the forecasted PV power and the deficit power. So this red one or the maroon one is basically the deficit power is showing deficit power. So it could be either positive or negative. So sometime I may have some excess power, but most of the time I have some deficit power. Okay, so deficit power negative means I have excess power, and deficit power positive means I need to depend on the storage or maybe on the utility grid. Now, this is the background that has been created for the study. So all this data and everything are being exchanged with the control room, and from the sensing points, they are communicated. So now it is being considered that everything is fine. It is working fine. Whenever there is a need, I can take power. Whenever there is an excess power, I can push power to the grid and can enjoy some incentive. So all these things are quite well, unless and until there is somebody who will tamper the data. Okay, so for the time being, let us consider that for workflow of that FDI attack approach, we just divided the prosumers into clusters: the low consumption group and the high consumption group. Okay, the low consumption group means which is having less than 10 kilowatt of that demand can be considered the low consumption group, and the high consumption is more than 10 kilowatt. So these are the two different categories of load, and the demand response percentage is also being decided based on whether it is LCG or HCG. So the minimum and maximum is varying from 5 to 15% for LCG and 10 to 30% for HCG. So more reduction is expected from that HCG. So more incentive can be given, and more reduction is expected. So 10% to 30% is that window, and 5 to 15% is the window for that LCG. Right. So we have that load demand response model. The demand is now catered if it is being there is some need of that battery integration. So we're depending on that BS model, and there is also some degradation model also being considered here, which is not the scope of the discussion today. So the BS power and this power is being considered by the service provider, and whether there is a need of exchange of energy with the utility in either direction, that can be decided. So electricity price is that black arrowhead is showing that electricity price, and the power flow is this red arrowhead or the orange arrowhead is showing the power flow. Okay. So what is my grid power? Grid power is basically the load, if it is taking part in the demand response we considered, minus the generation by PV and also the generation from the battery. So that much power we are basically borrowed from the grid. Okay. Now consider there is an attacker in the prosumer end. Okay, there is an attacker in the prosumer end. So what is the aim of that attacker? What is the aim of that attacker? And maybe attacker in the service provider end, right? So what could be the aim of that service provider? Obviously, both of them are looking at the monetary gain. Okay? Monetary gain. So how they could tamper the data, and what will be the impact on that dynamic pricing, and by which manner we can able to identify that false data, detect that false data. So we are having that policy of incentive-based demand response (IBDA) program for hierarchy prosumer clusters. So proposed year policy can be explained through this. Suppose we are having that critical window like this much T, where there is this particular time period, 30 plus 20 minus 2. This forward and backward of this particular time period is considered to be as a total 5 hours as the critical window. Why we have considered this as critical time window? This is the price which is peak at this point. Price which is peak at this point. Okay, so the consumer will be very much eager to reduce their load during this peak price period, right? So the maximum demand of all these clusters all these clusters is being shown here. C1, C2, C3, C4, C5, C6, C7, C8. Out of these 8 clusters, 4 are high consumption group. These yellow and the blue are the low consumption group. C3, C4, C6, C7. They are the low consumption group. So how much is the total connected load and how much is the maximum demand? So the demand factor is considered to be 0.75. Now, what is the IBDR policy? There are certain scenarios that has been considered in this study. So if a new demand falls above DR minimum, right? So you see the figure, it will be explained, it can be explained better. So this is my, this bottom line is the DR maximum, right? So this is the load demand. You can reduce maximum we are expecting that you can reduce up to this. The upper one is your actual demand, which is predicted basically, which is predicted. And we're expecting that you can reduce your demand at the bottom line, and in between there is the DR minimum. So you can reduce minimum this and can maximum this. Beyond this, we don't bother. That you can, if you wish, you can reduce. But if you are reducing something like that, you are taking part, but you are not touching the minimum DR also. So in that scenario, if the new demand falls above DR minimum, so that's the scenario. Okay, so these dotted red dots are showing that blue line is that I'm not taking part in demand response. I'm just predicting that this is my demand, and if I'm taking part during that time window, and if my reduction in that demand response while I'm taking part in the demand response, my reduction is something which is not touching even the demand response minimum what we have set for, right? You can remember that 5% and 15% for the LCR and 10% and 30% for the HCG. So what could be the incentive and what could be the penalty that has been decided from this formula, right? The second policy is that which is expected, that that customer has reduced its demand and which is in between the minimum and maximum. Then what could be the incentive, right? What could be the incentive that has been shown here? And the scenario C could be that even the customer is very readily taking part and then reduced beyond the maximum line. Then what could be the way that I will select the incentive. So based on that, this equation will decide that how much could be the incentive, right? Now, as I told you that the revenue and the benefit that we need to look at such that the service provider should not be in a situation that the profit is less than the incentive is more. Okay. So there is a crossover point. So we can day-ahead electricity price depending on that the 3 times, the 3.5 times, 3.75 times, 4 times, and 5 times. So these are the incentives that are being decided. So whatever is the day-ahead electricity price, if you take part in that demand response, you will get incentive either 3 times or 3.5 times or 3.75 times or 4 times or 5 times. That operator will decide. And it has been seen that if it is being selected for this particular study mandate, the similar scenario can be created for any such study. If it is being selected somewhere at 3.75 times of the day-ahead electricity price, then we are in a position that that your benefit and revenue, will not create, will not cross over yet. Okay, will not cross over yet. So this intersection of your service provider revenue and the prosumer cluster benefit acts that crossover point need to be the deciding factor. Okay, so my benefit should not be, the consumer benefit should not be more than the service provider revenue, right? So this is just an example for a cluster 5. Yeah, any question? So this is for the load profile for the high consumption group. The IBDR policy is being applied for all these clusters, which are HCG group. And this is shown here that what is the aggregated revenue and benefit. Right, every time obviously we'll see that the benefit is less than the revenue, and that's what the win-win situation is taken place. The customer is happy, and service provider is also happy, right? So you can see that actually that your electricity bill for all these, ultimately that incentive, putting these incentives, how much is the service provider revenue and what is the benefit that is being there. This particular customer, without DR and with the DR, there is a difference, and there is a difference in bill. Along with that, that much is the incentive they are getting. So this is the benefit. This is the total benefit. Okay. Is it clear, na? Because I reduce the load, so my bill at the end of the month will be less. And at the same time, I'm gaining some incentive, so my benefit will be added with this incentive plus this reduction. Okay. This is for the LCG. The similar scenario has been shown for all the 4 clusters of LCG. Now coming that that attacker is now there. So it could be the security assessment can be done on the pillars of the information security can be considered as that, whether it is how much it is available, what is the confidentiality, and how much there is an integrity. Okay, so all these 3 are the security assessment. On that basis, you can assess the security. So what could be the vulnerability and the communication channel, and the driving force is this communication technology behind the smart grid operation. So we can tamper the meter infrastructure and can take place via the communication channel, and can mislead the information for basically taking part in the market participation, and for at the end some monetary benefit. Okay, but the thing is that the attacker must be to the vicinity of the network. Unless and until the attacker is in the vicinity, it cannot take part in that tampering the communication. So first scenario, attacker is a part of any of the prosumer cluster. What will happen then, right? So what is the thing being done by the attacker is that some false data is being injected. So I have reduced this much, and I'm just tampered the data and shown that I have reduced much more. Then I will get some more incentive, and the bill will be less also. So I'll benefit. My benefit will be more. So what will happen after that FDI attack? So this is my maybe my demand response when it is being taken place. So I have reduced this much. I have shown that I have reduced this much. So there is a difference. The red dot is when the data has been tampered. And you see that the benefit becomes more than the revenue, which is not at all before FDI and after FDI. It is clear that this is not at all a scenario which is acceptable. Okay, which is acceptable. So it is easy for the attacker to identify also in that case, that wherever the cluster is getting more benefit than the revenue, then obviously something has happened, and it is easy for the operator to identify that. So what could be the other way that the attacker can think of? So I have tampered not only my data points, I'll tampered all the data points the other in my group. So I have reduced something, I have reduced some more, and this reduction is being distributed among the other clusters. Okay, so at the end, from the aggregated revenue and benefit, the after FDI and the modified FDI, you'll see that there is hardly any difference between the benefit and the revenue. Okay, so there is a less chance that the attacker would be identified. Okay, there is hardly any difference between these two, and it may seem that maybe there is a less benefit also. But the attacker is gaining. Attacker is gaining because it is distributed. But the other clusters are really affected. Okay, so their benefit has decreased and the attacker benefit has increased, considering that C1 is the attacker. Okay, so it is easy to identify from this table, but it's not so easy if it is happening in reality. The scenario 2 is that attacker is in the service provider end. Okay, so again, even if I am taking part in the DR and I have reduced something, but it has shown that the reduction is not that much. Okay, So in that way, I can tamper the data and can say that that particular attacker will not get that much revenue, that much incentive, and there is a win-win. There is a win situation or the gaining situation from the service provider end. So that can also happen. So there is always some reduction in there by the wish of the customer, but it has been tampered. Everywhere some tampering has been there, and what was the actual one is not being shown. That the red dot during that critical time window can be seen that they are all above the blue line, right? So the load demand profile that for HCG and LCG are being shown if the attacker is at scenario 2 or the attacker is at the service provider end. So what will happen? All the benefits will decrease. All the benefits will decrease. Okay. So whatever the difference between before FDI, the revenue and the benefit, that difference was going on increasing. So the service provider can enjoy this more power for this is for HCG and this is for LCG. Okay. So this could be the scenario. This could be the scenario. So how to identify? So I need to identify that this is a malicious operation or not. So whether it is a normal or attack. So I'm basically classifying it. So now this machine learning based the aim of this machine learning is the classification problem, whether it's a normal or attack. It's not a forecasting problem. Okay. So how this has been done? So there are certain steps. So we are monitoring the load demand of each of the cluster. And then the net load monitoring is being there for monitoring the cumulative SPR and the PCB, the benefit. So we're deciding the revenue and benefit. And then always there is a chance that the meters has some kind of an accuracy limit. So we consider that the smart meters has some error band of 2.5% plus minus 2.5%. So that variation is under consideration. If that could be the scenario that there is some error in the smart meters. So which is not, of course, cannot be considered as an attack scenario, which is still as a normal scenario. So that is again considered, and labeling of the target variables as normal or attack. So this is how the things should continue. Okay, for this classification purpose. So DR event is this region. So we are seeing here that the service provider revenue and the prosumer cluster benefit. Okay, the blue line is for the revenue and the orange line is for the benefit has been shown for 2 random days from the data set. 2 random days. So we are just finding out for classification purposes that the binary classification with the help of this confusion matrix, that it is true positive or true negative, false positive or false negative. So the accuracy is depends on that how much is the true positive plus true negative divided by the total samples. So and TPR is the true positive rate is the true positive divided by the false negative plus true positive. So true positive means it is normal and it is predicted as normal. False positive, false negative, true negative, right? So this is the way that the confusion matrix is being formed, and then the accuracy is depending on the. So in which manner that what ML algorithm are being used? There are several ML algorithm has been tried, and then ultimately we are using some hybrid and ensemble model with some weightage. Okay, so random forest, and then there is a decision tree, then there is k nearest neighbor, then there is support vector machine and naive Bayes. All these 5 methods are being used, and they are weighted. How these weights are being decided, I'll just let you know. And then this weighted voting has been done, and ultimately we are basically giving the weightage of each of these machine learning techniques, and ultimately consider it as a normal or maybe attack, then it will raise some alarm. Okay, so the ML parameters is being shown here in this table. Now, how the weight has been decided. So individual models are assigned with some weight, right? So the change in the weight is decided based on that what is my TPR. the true positive ratio, divided by the summation of TPR divided by the, or basically the average of the total number of the TPR classifier model. If the classifier model here it is 5, so summation of TPR divided by 5 is what's the average. So TPR of a particular ML model divided by the average for all the models is being considered as the change in the weightage. So we initialize some weight to each of the classifier, and then we just perturbed with the help of this change in weightage, and then the new weight has been decided, right? So when this new change in weight is being added with this initial weight, we are getting some good results. And as we can see from the result scenario, that the accuracy is quite good. As far as the TPR is also quite reasonable. Now, the average TPR for the base model is found to be 0.9375. It has been seen that the random forest is showing good result for the attack scenario 1, and naive based is for the attack scenario 2. But how can I understand that whether it is attack from the prosumer end on the service provider end? So that's why it is that weighted ensemble model has been used. So all the goodness of each of the models are being collected and weighted and considered. So overall average TPR is become 0.935, and the proposed hybrid weighted voting algorithm is giving the accuracy for the scenario 1 as 0.973 and for scenario 2 as 0.918. Okay, so it is shown that the undetected instances decreases from 3.2% to 2.6% for scenario 1, and the undetected instances decreases from 19.6% to 10.4%, right? So it's from the default weights to the modified weight. So that's the advantage of this weighted voting algorithm, ensemble algorithm. Fine, so that's the end. So there are a lot of works which not obviously I was a part of that team, and so I should thank my students, Vaishnavi and Shreya. They are the BTech student. The first one, which was basically being that tool for that energy management and DR response for the demand response for the utility and the that consumer, being entirely developed by these BTech students through their BTech final year project. So I'm really grateful to them, Vaishnavi and Shreya. The next part, this IVDR policy and FDI attack scenario, is one of the chapters of one of my PhD student, Dipanshu Naure, who is now faculty at NIT Trichy. And Kamini was my research fellow who has worked for that DM part project. So she has developed that forecasting models for those 4 locations of the sites, and Dipanshu is mainly working on this FDI attack scenario and that battery degradation model and all. So I just taken their work and presented here for you people for this particular FDP. So I believe that you enjoyed, and thanks for your patient listening. Thank you.
Thank you so much, sir, for your insightful and technically rich session. Now we have opened the floor for the question and answer session. So I would like to request the participants to please proceed further with the questions.
So I apologize for extending my presentation beyond the time limit of 7:30.
Hello.
Yeah, hello.
Yes, participants, do you have any questions? Please move ahead.
Sir, one question, sir.
Yeah.
Sir, in the plot section, sir, you consider the timeline for the PV cell uh, 10 a.m. to like 9 p.m. So the location was like sunrise is at 10 a.m. or sunset is.
So this is not actually the location is the second part you are talking about, right?
Yes, sir. Yes, sir.
Yeah, that particular location is not in Asia actually. It is in Panama region. It is in Panama region where the load are being taken from that region. So the solar insolation forecasting has been done for that region only. So that is how it is a bit different from the actually we are seeing in this Indian region. A bit different. That's the thing.
Oh,
Yeah, if there is no other question, so I can consider this is the end of my session.
Okay, so since the participant doesn't have any questions, so we are closing the question and answer session. Thank you once again, sir.
Yeah, thank you very much for inviting me for this wonderful FDP. So enjoy
Thank
the sessions of this FDP, and I believe that you will obviously gain something and can take away of this session would be your the future research direction and the future research topic.
Sure, sir. So just
Okay.
one request.
Yeah.
I would like to request everyone to please switch on your camera. We have to take the screenshot. Sir, if you
Sam?
can,
Yeah.
yeah.
I've stopped my
Thank you, sir.
presentation. Thank you. So I just want to mention here one thing. Bimanda is one of my mentor at IIT Kharagpur. He was my lab mate. So I learned a lot from him. Thank you, Bimanda.
Thank you also for giving this session, giving the presentation in this session.
Thank you.
Okay, thank you all. Thank you all.
Thank you.
Thank you, sir.
Bye, everybody.